Focus is not simply a matter of discipline or motivation, it is a biological process, a function of the brain, body, and environment working in concert. Every decision you make, every task you attempt, and every moment you spend learning or performing depends on your ability to direct attention effectively. Focus is not merely a matter of willpower or discipline, it is a biological function governed by specific neural networks in your brain. The prefrontal cortex, the parietal cortex, and subcortical structures like the thalamus and basal ganglia all interact to determine what you pay attention to for how long and with what intensity. Understanding these networks is crucial because it means focus is not abstract, it is measurable, trainable, and influenced by concrete behaviors. The brain operates as a complex system in which certain neurons fire to enhance attention while others inhibit distractions. When these systems are synchronized, you experience what neuroscientists call laser focus, a state where your mind filters out irrelevant information, owns in on the task at hand, and sustains performance at a high level. This is not about trying harder. It is about working with the brain's natural architecture and its chemical signaling pathways. Neurotransmitters like dopamine, norepinephrine, and acetylcholine play key roles in modulating attention. Dopamine, for example, is often associated with reward and motivation, but it also functions as a precision signal for focus. When dopamine levels are balanced, your brain can signal clearly which tasks are relevant and which stimuli should be ignored. Norepinephrine is released during states of alertness, heightening sensory perception and readiness to act. Acetylcholine, on the other hand, strengthens the connections between neurons involved in sustained attention and learning. These chemicals interact dynamically, and the balance among them is critical. Too little, and your mind wanders too much, and you experience anxiety and scattered attention. By understanding these mechanisms, you can learn to modulate your state physiologically, not just mentally, setting the stage for optimal focus. The brain's attention networks are also influenced by external sensory inputs, particularly vision. How you orient your eyes in space, how you manage visual clutter, and how you control what enters your visual field all directly affect neural firing patterns. Our brains evolved to prioritize visual information because it was essential for survival, and the same systems now determine how we process tasks, detect threats, or filter distractions in modern environments. By consciously managing what you look at, how you scan your environment, and where you direct your gaze, you can engage the neural circuits responsible for selective attention. This demonstrates that focus is not an abstract concept. It is an embodied, physiological process that can be shaped and reinforced with practice. Another critical component is the temporal structure of focus. The brain does not sustain peak attention indefinitely. Neural circuits operate in cycles of high alertness and recovery, often ranging from 60 to 90 minutes. Understanding this biological rhythm allows you to work with your brain rather than against it. Structuring your day to align demanding cognitive tasks with your natural cycles maximizes performance and reduces mental fatigue. Ignoring these cycles leads to scattered attention, reduced efficiency, and cognitive burnout even for individuals with strong motivation or discipline. Finally, focus is reinforced through practice and deliberate activation of the relevant neural networks. Just as a muscle grows stronger with repeated use, attention networks strengthen when challenged appropriately. Cognitive exercises, mindful engagement in complex tasks, and consistent reduction of distractions train your prefrontal circuits to operate more efficiently. This principle of neuroplasticity shows that focus is not static, it is an ability that can be expanded, sharpened, and optimized over time through scientifically grounded methods. Visual and environmental cues are powerful determinants of your ability to focus because the brain relies heavily on sensory input to prioritize attention. Your eyes are not passive observers. They actively guide neural circuits in the prefrontal cortex, parietal cortex, and subcortical structures to determine what matters and what can be ignored. When your visual field is cluttered or filled with irrelevant stimuli, your brain is forced to filter and suppress excess information, which consumes energy and reduces cognitive efficiency. Conversely, by intentionally managing your environment, removing distractions, structuring your workspace, and optimizing lighting, you signal to your neural networks that certain inputs are relevant, enhancing the precision of attention and engagement. This principle is rooted in the way the brain evolved. Our ancestors' survival depended on the ability to detect threats and opportunities visually while ignoring irrelevant noise. Today, this translates into modern practices for productivity and focus. Environmental cues also influence neurotransmitter systems. Dopamine, norepinephrine, and acetylcholine are all sensitive to context, meaning that the space around you can either amplify or suppress the brain's capacity for sustained attention. Bright, natural light enhances alertness by regulating circadian rhythms and triggering norepinephrine release, which primes sensory circuits for action. In contrast, dim or inconsistent lighting can create a subtle signal of lethargy or disengagement. Similarly, environmental sounds, both intentional and unintentional, affect neural attention networks. Background noise can either enhance focus, as in certain rhythmic patterns, or white noise, or fragment it, as in unpredictable or highly salient sounds. By controlling environmental cues, you align physiological systems with cognitive goals, transforming spaces into tools rather than obstacles for attention. Our brains are wired to assign priority based on context and expectation. When you consistently place objects, screens, and tasks in predictable locations, the brain learns to anticipate relevant inputs and ignore irrelevant ones. For instance, keeping your phone out of sight while working allows neural circuits to avoid constant salience checks, reducing the number of micro distractions that fragment attention. Visual cues also shape habit formation. Seeing a task list or a specific tool in the workspace can trigger dopamine release, motivating engagement and maintaining attention. This interplay between environment and neurochemistry shows that focus is not just a mental effort, it is an embodied, context-dependent process that can be sculpted deliberately. The spatial and temporal arrangement of environmental cues also matters. Cluttered or unpredictable surroundings demand cognitive resources for constant assessment, engaging the dorsolateral prefrontal cortex in a reactive mode rather than a proactive, goal-directed mode. When the environment is structured to reduce irrelevant visual load, the brain can allocate resources efficiently, sustaining high-level attention for longer periods. This is why expert performers, from athletes to scientists, often engineer their environments meticulously. Every element is positioned to support desired neural patterns, minimizing friction and maximizing engagement. Finally, the principle of sensory gating highlights how the brain selectively filters inputs to maintain focus. Neural mechanisms in the thalamus act as gatekeepers, allowing certain stimuli to pass through while blocking others. By consciously controlling visual and environmental cues, you strengthen the brain's natural gating mechanisms, enabling prolonged concentration and deeper cognitive processing. Over time, repeated exposure to optimized environments trains attention networks, increasing their efficiency and resilience to distraction. Understanding and applying this concept means that focus is no longer left to chance. It becomes a controllable, biologically informed skill that shapes your productivity, learning, and performance. Stress and cortisol have a profound impact on cognitive performance and focus because the brain's attention networks are highly sensitive to physiological states. When the body perceives a threat, real or imagined, the hypothalamic pituitary adrenal HHPA axis is activated, releasing cortisol and other stress hormones. In moderate amounts, this system enhances alertness, sharpens perception, and primes the brain for rapid response. However, chronic or excessive stress leads to persistent cortisol elevation, which can impair prefrontal cortex function, the very region responsible for sustained attention, decision making, and impulse control. The result is a paradoxical effect. The systems designed to enhance focus under pressure become dysregulated, leading to scattered attention, mental fatigue, and decreased cognitive efficiency. Understanding this relationship is critical because it shows that focus is not simply a mental skill, it is deeply intertwined with the body's stress physiology. Cortisol interacts with neurotransmitter systems in complex ways. Elevated cortisol reduces dopamine signaling in prefrontal circuits, which diminishes motivation and the precision of attention. It also affects norepinephrine levels, which can either heighten distractibility or create hypervigilance, depending on the context. Chronic stress can lead to structural changes in the brain, including reduced dendritic branching in prefrontal neurons and increased amygdala reactivity, both of which make sustained focus more difficult. These biological mechanisms illustrate why people under prolonged stress often feel foggy, struggle to concentrate, or experience cognitive lapses despite trying to engage intentionally. The solution is not merely mental effort, but interventions that target both physiology and neural circuits. Behavioral and environmental strategies can regulate stress and optimize focus. Controlling breathing patterns, for example, has a direct effect on the autonomic nervous system, reducing sympathetic overactivation and lowering cortisol levels. Techniques such as slow, diaphragmatic breathing or cyclic breathing stimulate the vagus nerve, which signals the brain to shift from a state of high alert to one more conducive to sustained attention. Physical movement, particularly aerobic exercise, modulates HPA axis activity and enhances dopamine and norepinephrine signaling, improving both mood and attentional precision. These strategies demonstrate that focus is not simply a cognitive process, but a biologically embedded skill that can be influenced by deliberate actions in daily life. Sleep and circadian alignment further mediate the impact of stress on attention. Cortisol naturally follows a daily rhythm, peaking in the morning and declining toward the evening. Disruptions in sleep patterns or exposure to inappropriate light cues can desynchronize this rhythm, leading to elevated evening cortisol and reduced prefrontal cortex function the next day. By regulating sleep timing, exposure to natural light, and evening behavior, the brain's stress response is optimized, allowing attention networks to function efficiently. This interplay of stress, neurochemistry, and environmental cues underscores the importance of a holistic approach to focus, where the body and brain work together rather than in conflict. Understanding the influence of stress on attention also highlights the necessity of deliberate recovery. Periods of rest, meditation, or low stimulation activity allow cortisol levels to normalize and prefrontal circuits to recover. Incorporating these recovery windows into work or learning schedules maintains optimal brain function, prevents cognitive fatigue, and preserves the capacity for deep, sustained focus. Over time, managing stress physiologically trains neural circuits to remain engaged under challenging conditions, creating resilience and enhancing overall mental performance. Focus, therefore, is not merely a product of effort. It is the outcome of finely tuned biological systems interacting with behavior, environment, and conscious strategies. Neuroplasticity is the cornerstone of training your brain to sustain prolonged focus. Because attention is not fixed, it is a skill that can be strengthened through repeated, deliberate activation of relevant neural circuits. The brain's prefrontal cortex, parietal cortex, and associated subcortical structures are highly adaptable, capable of forming new synaptic connections, reinforcing existing ones, and optimizing network efficiency based on repeated experiences. Each time you intentionally direct attention to a task, you are not just exerting willpower, you are remodeling the architecture of your brain, strengthening the pathways that support sustained focus. Over time, these circuits become more efficient, more resilient to distraction, and capable of longer periods of deep engagement. This is the biological basis for mastery, learning, and high-level performance across domains. The principle of neuroplasticity operates through what neuroscientists call Hebbian learning, often summarized as neurons that fire together, wire together. When you repeatedly engage attention networks while minimizing interference from irrelevant stimuli, synaptic connections between neurons involved in task-relevant processing are strengthened. This results in faster information processing, enhanced working memory, and greater ability to filter distractions. Conversely, neglecting focused engagement or consistently succumbing to interruptions weakens these circuits, making it harder to sustain attention and increasing susceptibility to mind wandering. By understanding this, focus can be approached systematically as a trainable skill with measurable biological underpinnings. Timing and repetition are critical for neuroplastic adaptation. Short, intense bouts of focused attention followed by recovery periods optimize synaptic consolidation and prevent cognitive fatigue. The brain naturally cycles through phases of heightened alertness and recovery approximately every 60 to 90 minutes, a rhythm that can be leveraged to maximize learning and focus. When attention training aligns with these natural rhythms, neuroplastic changes are accelerated. Ignoring these cycles leads to diminishing returns, cognitive burnout, and decreased neural efficiency. Structured focus sessions, often referred to as attention sprints, followed by periods of deliberate rest, create optimal conditions for strengthening attention networks. Stress and arousal levels further influence neuroplasticity. Moderate controlled stress releases norepinephrine and dopamine in ways that enhance synaptic plasticity and learning, while chronic or excessive stress impairs these processes. This means that cultivating an optimal physiological state through breathing, movement, and environmental management is essential for neuroplastic growth. The brain requires both challenge and safety to adapt effectively. Challenge stimulates neural change, and safety allows consolidation of those changes. By intentionally modulating arousal and stress levels, you provide the ideal environment for attention networks to strengthen and for focus to become more robust. Behavioral habits reinforce neuroplastic adaptation. Minimizing multitasking, eliminating unnecessary distractions, and intentionally practicing deep work create conditions for sustained attention. Engaging in mentally demanding tasks repeatedly while maintaining physiological readiness accelerates synaptic remodeling in circuits responsible for focus. These habits become self-reinforcing as attention networks strengthen, focus improves, which in turn allows longer and more effective training sessions. Neuroplasticity demonstrates that sustained focus is not a static trait. It is a biologically modifiable skill that grows with consistent, deliberate practice and appropriate environmental and physiological support. Sleep and circadian rhythms are critical regulators of mental clarity and sustained focus because the brain relies on precisely timed physiological processes to consolidate memory, reset neurotransmitter levels, and maintain neural network efficiency. The prefrontal cortex, responsible for sustained attention and executive function, is particularly sensitive to sleep deprivation or circadian misalignment. When sleep is insufficient or irregular, the brain experiences reduced dopamine and norepinephrine signaling, diminished synaptic plasticity, and impaired filtering of irrelevant stimuli. This leads to scattered attention, difficulty concentrating, and an overall decline in cognitive performance. Understanding and respecting these biological rhythms is not optional, it is fundamental for optimizing focus and cognitive resilience. Circadian rhythms are governed by the suprachiasmatic nucleus in the hypothalamus, which synchronizes neural and hormonal activity to the natural light-dark cycle. Exposure to natural light in the morning stimulates cortisol release and primes attention networks for the day, enhancing alertness and task engagement. Conversely, exposure to bright artificial light late at night or irregular sleep-wake cycles can disrupt melatonin production, impairing both sleep quality and the prefrontal circuits responsible for focus. Aligning daily schedules with circadian cues, such as morning light exposure, consistent wake times, and limiting evening light interference, supports optimal neural function and strengthens the capacity for sustained attention. Sleep itself plays an essential role in consolidating learning and attention. During deep non-REM sleep, The brain strengthens synaptic connections in circuits involved in attention, memory, and problem solving. REM sleep further enhances cognitive flexibility, emotional regulation, and the ability to prioritize stimuli. Insufficient or fragmented sleep prevents these processes, weakening attention networks and making it difficult to filter distractions or maintain prolonged focus. Chronic sleep disruption not only impairs cognitive performance in the short term, but also increases the risk of long-term structural changes in the prefrontal cortex and hippocampus, demonstrating that sleep is a critical biological investment in mental performance. The interplay between sleep, circadian rhythms, and focus extends to neurotransmitter regulation. Adequate sleep replenishes dopamine, norepinephrine, and acetylcholine in attention circuits, restoring precision and reducing mind wandering. Sleep-deprived individuals often experience heightened amygdala reactivity, which increases sensitivity to perceived threats and distractors, further compromising focus. Aligning sleep and wake cycles with natural circadian rhythms ensures that neurotransmitter levels are optimized for both alertness during the day and recovery at night. This creates a stable platform for cognitive performance and sustained attention. Behavioral strategies to support sleep and circadian alignment are simple yet powerful. Morning sunlight exposure, limiting caffeine or stimulants too late in the day, consistent bedtime routines, and a cool, dark sleeping environment all enhance sleep quality and, by extension, neural readiness for focus. Naps of 20-30 minutes can also provide targeted replenishment for attention circuits, particularly when timed strategically during natural dips in alertness. By respecting the brain's biological timing and prioritizing recovery, individuals can maintain peak attentional performance, resist fatigue, and achieve deeper, longer, lasting engagement in tasks. The science is clear. Focus is not solely a matter of effort or willpower. It is inseparable from the brain's physiology, circadian rhythms, and sleep architecture. Optimizing these systems creates the foundation for reliable, sustained attention, enabling peak cognitive performance and the ability to engage deeply in meaningful work. By aligning behavior with biology, the brain's attention networks can operate at maximal efficiency, transforming focus from a fleeting resource into a consistent, trainable skill. Practical behavioral strategies are the final piece in mastering laser focus because the brain's attention networks, while biologically grounded, respond dynamically to intentional action. Attention is not passive. It is shaped by habits, routines, and environmental choices that either strengthen or weaken neural circuits responsible for sustained engagement. Deliberate behaviors, when aligned with the brain's physiology, act as levers to enhance focus, resilience, and cognitive efficiency. These strategies translate scientific understanding into actionable steps that anyone can implement, allowing the principles of neuroscience to become tangible tools for mastering the mind and optimizing performance. One foundational strategy is to structure the environment to reduce distractions and signal relevance to the brain. Visual and auditory clutter consumes neural resources and activates filtering systems in the thalamus and prefrontal cortex, fragmenting attention. By creating a workspace where irrelevant stimuli are minimized, your neural circuits can allocate energy toward task-relevant processing. This includes controlling lighting, managing background noise, and organizing materials to match workflow demands. Each environmental adjustment sends a signal to the brain that certain inputs are important, reinforcing selective attention and improving precision in cognitive tasks. Another critical behavioral approach is managing temporal focus through structured work periods. The brain naturally cycles through peaks of alertness and recovery approximately every 60 to 90 minutes. Aligning demanding cognitive tasks with these peaks maximizes neural efficiency, while deliberate breaks allow neurotransmitter systems and synaptic circuits to recover. Short, focused sprints followed by intentional rest periods enhance neuroplasticity, strengthen attention networks, and prevent cognitive fatigue. Ignoring these rhythms often leads to diminishing returns, where effort increases but performance decreases, demonstrating that behavior must be coordinated with biology for optimal focus. Mindfulness and deliberate breathing techniques also provide behavioral leverage over attention. Practices such as deep diaphragmatic breathing or cyclic inhalation, exhalation patterns modulate the autonomic nervous system, reducing sympathetic overactivation and lowering cortisol. This creates a physiological state conducive to sustained focus, allowing the prefrontal cortex to operate with minimal interference from stress or anxiety. Combined with meditation or mindful attention exercises, these behaviors train the brain to remain engaged despite distractions, enhancing both the depth and duration of cognitive performance. Behavioral strategies extend to habit formation and the sequencing of tasks. Prioritizing high-value tasks first, minimizing multitasking, and batching similar activities help the brain focus efficiently, leveraging dopamine signaling to reinforce engagement. Reward structures, both internal and external, can be used intentionally to maintain motivation, activate attention circuits, and sustain energy for prolonged cognitive work. Over time, these behaviors strengthen the neural architecture underlying focus, transforming temporary states into reliable skills. Finally, consistent practice of these behavioral strategies interacts synergistically with sleep, circadian alignment, stress regulation, and environmental management. Focus becomes not a fleeting trait, but a trainable system that integrates physiology, behavior, and context. Each deliberate action, whether controlling the environment, structuring time, managing stress, or reinforcing habits, enhances the brain's capacity for sustained attention. This demonstrates that mastery of focus is not abstract or mystical. It is rooted in biology and empowered through consistent, science-based behaviors. When implemented systematically, these strategies allow the mind to operate at its highest capacity, creating the conditions for productivity, learning, and peak performance